Okay, so let's imagine a scenario where we've just all done a test for Mr. Wood, and he was very impressed by our scores. He was so impressed that he bought 4 whiteboards, put them up in his room, and wrote the name of each person based on their results. So these kinds of whiteboards, basically. And he wrote each person's name on each whiteboard. What you would have is basically this. A list or a series of names of people based on how well they did. So obviously Rob did the best because he's the genius in here. This is essentially an array. The core parts of an array are the fact that you can modify the value at any index. So Mr. Wood could rub out the whiteboard and put someone else's name there if someone else did better. They can be fixed or variable length. Mr. Wood's whiteboards are fixed length because he only has 4 of them. 0 indexed. This is this row here. So humans would label Rob number 1 because he's the best. But computers start with 0 when they are talking about arrays. And there are some other facts about arrays that are specific to arrays. For example, if you wanted to insert someone in, like someone did the test a day late, and they happen to do it better than Alex, Mr. Wood would have to write their name here, then change this one, then change this one. So he would have to go through every single one and change them if he wanted to insert. That means that insertions into arrays are kind of slow. But if you wanted to read the name of any specific person, he would be able to go straight to that whiteboard. So indexing is quick. Now an array is an example of both an abstract data type and a data structure. And there's a difference there. So an abstract data type is what happens when you take your primitive data types, which are int, char, and similar things like that, which are literally stored in the computer's memory, and you combine them together and structure them. You get an abstract data type. And the abstract data type of an array has these properties. When it turns into a data structure is when it's actually implemented in a language. So when we actually use arrays in C, or when we use lists as arrays in Python, that is a data structure. So abstract data type is the concept of an array. Data structure is the implementation of an array. Which, here's an example of an implementation. Python has lists, which are not just arrays, but they can be used as arrays. If we set the array like this, we can go and access the value of any index, and we can overwrite the value at any index, just like with the whiteboards, where you could rub it out and change it for any specific index. And that's a completely implemented array in Python. We don't actually have to do anything. Strings, by the way, this is interesting. Strings, I didn't mention strings as a primitive data type, even though we've been using them, because strings are actually an array of characters. Fixed length of characters, or in Python they happen to be fixed. In other languages they could be mutable, so not fixed. And you can access the value at any index, just like an array. So now we've got another data type, another abstract data type, which is a quite simple one. This is called a queue, and as you can guess, the example I'm going to give here is that we're all standing in line for lunch. So this is what it would look like. Now queues in real life work in the sense that one person enters the queue, and that person would be the first one to exit the queue. So if I queue up, and then Will queues up, and then Mr. Wood queues up, and then Anushka queues up, whenever the food is ready, the first person to get the food will be me, because I was there first. This is known as first in, first out. And these are the operations you can do on a queue. You can in-queue and de-queue, and that's it. You can only add to the queue, remove from the front of the queue. You can't see who's in the queue, necessarily. For example, the person giving the lunch might not be able to see who's further back in the queue, other than the first person. And you can't change anybody in the queue. So this is the concept of the abstract data type known as a queue. And here's an implementation of a queue in Python. If we make the line like this, we have a function here built into Python called pop, which removes an item from a list and returns it. If we do pop 0, it returns the item at index 0, which in this case happens to be the first person in the line. If you take the first as the left. If you take the first as the right, then you would pop from the right. And then append adds to the end of the line. So if we pop and then append Hugo, the line will now look like this. Again, the main point here is that the abstract data type of Q has specific properties. The implementation doesn't really matter as much because that depends on the language. So this kind of stuff will be different from language to language. The most important thing is that a Q has these features. And now, the final data type, which can be kind of more complicated than the other two. We'll have a new scenario. Let's say you want to take a flight, and you go to the flight, and they say you need to buy a ticket first. So then, you go and find out how you need to buy a ticket. You go to the ticket office, and they say you need to renew your passport because it's expired. So you go to the passport office, and they say you need to get a new passport photo because this is too old. So now, in order to fly, first you have to renew your ticket. But before that, you need to renew your passport. But before that, you need to get a new passport photo. So these tasks have kind of stacked up like this. You have to do all these things in order to fly. This data type obviously is known as a stack. And what happens is something gets added to the top of the stack and then removed from the top of the stack. So all you can do is push onto the stack or pop from the stack. For example, in this example, when you are going to renew your passport, the guy at the passport office says, you need to get a new passport photo. That task was pushed onto the stack, and now when you actually get the passport photo, you'll pop it, you'll remove it, and then you can continue downwards. So similar to the queue, you cannot necessarily see what the members of the stack are other than the first one, and you cannot change any of the members of the stack other than the top one. Implementation of stack, super easy in Python. Append adds to the end of a list, and pop removes from the end of a list. So, the top line where task is defined isn't there, but basically, if this was the stack, you could push photo onto it and then pop photo off of it. Just like you would think about it in real life. Now, stacks are actually fundamental to how computers work and how programming works. Because if you think of these as functions, if you think of these tasks as functions and rewrite the stack like this is actually a model of how programming languages execute functions. It's known as the call stack. So imagine you call a function fly, and within fly another function is called, which is buy ticket. What happens is the program allocates new memory literally above in the stack. And then this function, buy ticket, has to be completed before fly will continue. So all of the function's data will be in this stack frame. And that's exactly what happens when you call functions inside of each other. It gets added to the call stack, it evaluates, once it's done, it gets pushed off the stack. And then you can continue with the previous function. So if you took your photo successfully, renewed your passport, bought your tickets, all these three would get pushed off, then you could successfully take your flight. And this is the concept of a stack, which is probably the most important data structure out of the three that I've talked about today. And that's pretty much it. Any questions regarding any of the specific slides or these implementations?
Have you got any examples of where you've actually had to use them in any programs you've written, Murtaza?
Queues and stacks themselves are not really super common in most of the programs that we would write. They're usually deeper down or for more systems level things. Arrays there are many examples of when an array could be used. Like this is a real example that you might actually see in a program if you have a list of names. Instead of having name 1, name 2, name 3, you just have names in one big array.
Could you explain to us the concept, and I remember you explaining this to me, that if you were talking about defining what an actual array was, and then you talk about Python's implementation of an array being the closest to a list you mentioned in this, but they're not the same, are they, if you were defining them? Because
they're not the same. So Python's list has things specified other than these functions. So in essence, the bare bones of an array is that it's a sequence of data which you can change at any point in that sequence. That's the only thing that's specified for an array, or that's the most common definition of the abstract data type, which is the array. In Python, there are many other things that you can do with lists that you couldn't necessarily do with arrays. Like these things, what I've put on this slide, indexing and setting something at an index, that is required for an array. So it's good that that's part of the list. But then if you go here to this slide, we've used the pop method and the append method. These are part of lists in Python, but they're not required for arrays.
What about the discussion we had about the storage of data within an array? And you were talking about the difference between a list and a tuple, and the idea of, you talked about previously accessing something in that array would tend to be quite quick. But if it was in a list, it wouldn't be as quick as it would if it was a tuple. Is that correct?
Right, so there's a number of things there. There is a data type, abstract data type known as a linked list, which instead of having whiteboards, as I said, it's like there's a bunch of boxes with string attached to other boxes. So if you don't know where the boxes are, which the computer wouldn't with a linked list, it would go to the first box, then follow the string until it reaches the box that it wants. But if it has all the whiteboards available, it can just point straight at the one it wants. So in an array, the indexing is instant, or it's in constant time, big O of 1. In a linked list, it'll be big O of n, the n being the number of items in that linked list. But a linked list is something that we'll discuss properly later.